This is a video on catalysis. So our aims for this video are to be able to understand what is meant by homogeneous and heterogeneous when applied to the catalysis, understand how most heterogeneous catalysts work and how they can become poisoned, understand how heterogeneous catalysts can be made more effective, understand how vanadium pentoxide catalyzes the contact process, know how to work out the reactions occurring when using a homogeneous catalyst, and understand what is meant by auto-catalysis and know the catalysis of the reaction between manganate ions and ethane dioate ions. So first, what is meant by the terms homogeneous and heterogeneous? And the difference between these two things, remember that homo means the same and hetero means different. So a homogeneous catalyst is where the catalyst and the reactants are in the same phase. So they're both liquids or they're both solids, they're both gases. And this usually means that both the catalyst and the reactants are in solution. A heterogeneous catalyst is where the catalyst and the reactants are in different phases. So usually a heterogeneous catalyst where the reactants and the catalyst are in different phases come in the form of a solid with a gas being passed along the top. So an example of this would be in the Haber process. I'm going to use the Haber process as the example to show you how heterogeneous catalysts work. So in the Haber process, iron is our catalyst. So what we'll have is a surface of iron, and we'll get the gases of nitrogen and hydrogen flowing over the top of them. And what will happen is the nitrogen and the hydrogen will stick to the iron. And we call this adsorbing. So the reactants adsorb to the catalyst. What then happens is the reaction. So on the surface of the catalyst, the reaction takes place. And so the catalyst basically brings these reactants together and allows them to react on its surface. So we then get the reaction happening. So they'll react to form the NH3. And then the NH3 is not as strongly held as the nitrogen and hydrogen, and that desorbs off the iron. The other example that may be familiar to you for a heterogeneous catalyst is the catalytic converter in a car exhaust. And both the catalytic converter and the iron in the Haber process can be poisoned. And poisoning occurs due to the fact that we have impurities in the reaction mixture. So with the Haber process, those impurities may be sulfur. And what sulfur does to the iron is it sticks to the iron, or it adsorbs the iron too strongly, and it won't come back off again. And that means that it's taking up active sites on the iron that could otherwise be used for reactions. So that's for the iron. The sulfur is the poison. And for the catalytic converter, lead is the poison. So for a platinum in the catalytic converter, lead can stick too strongly or adsorb too strongly to the platinum and not be removed. So poisons take up active sites or block active sites on the catalyst, which stops reactants being able to adsorb onto those active sites and partake in the reaction to form the products. Now, to stop this from happening, you can ensure that the reaction mixture that you put through the reaction is purified to remove any poisons that may be present. And that, well, if the poisons aren't there, then they can't poison the catalyst. So in the previous slide I showed the catalysts as just blocks, so for the iron and the platinum, and hopefully it's fairly obvious that if you increase the surface area of these, then i.e. break them up into pellets instead, then it should increase the effectiveness of them, because there are also lots of active sites within the iron that isn't exposed to the reactant. So if you break up the iron or break up the platinum, then you will increase the number of active sites. You can either do this by turning the catalyst into a powder, or at least breaking it down, or you can put the catalyst on a ceramic zeolite structure, which also, if it has a honeycomb structure, then that will also increase the surface area of the catalyst. So there are a number of different examples that you need to know of catalysts working, and one of those is vanadium pentoxide catalysed in the contact process. So the reaction in the contact process that actually gets catalysed is the sulfur dioxide reacting with oxygen, and it's actually in equilibrium with SO3. And the catalyst that's used just makes its equilibrium get to it quicker. And the catalyst that's used is V2O5. So the V2O5 in the two catalyst equations reacts with the SO2 to form SO3 plus V2O4, and then the V2O4 reacts with oxygen to form V2O5. So that's one pair of equations that you need to know for your exam. Another set of catalyst equations that you need to know relates to the following reaction. So S2O8 minus plus I minus goes to make 2SO4 minus plus I2. We need two iodide ions in order to balance that. And this is catalysed using iron. And the reason it needs a catalyst is because you've got two negative ions reacting together, which obviously will repel each other, and therefore the activation energy is very high. And the iron 2+ will catalyse the reaction because it is positively charged and therefore will attract the negative ions. And I'm going to show you the two catalyst equations, but I'm going to show you how to work them out rather than showing them you to learn, because it's very important, or at least very useful, for you to be able to work out these catalyst equations just in case you get stuck in the exam. So the first thing to do is to draw out the two half equations that form this redox reaction. So the one half equation is S2O8 minus going to form SO4 minus, and the other half equation is your 2I minus going to form I2. So we first balance the S2O8 minus one. So the first thing to do is balance anything that's not hydrogen or oxygen, so that's sulfurs, so we'll just multiply that by 2. And then now the oxygen's already balanced, and then we just need to add electrons. On the left-hand side, there is an overall charge of 2 minus. On the right-hand side, an overall charge of 4 minus. So we need 2 electrons on the left-hand side, and then to balance the second one, we need 2 electrons on the right-hand side. Now the thing that is catalysing this is Fe2+, and Fe2+ will turn into Fe3+ when it is catalysed, or when it, acts as a catalyst, and to balance this we need an electron on the right-hand side. Once you've got those three equations, you need to combine two of them, or at least one of your half equations from the fuller reaction with your catalyst equation. And the one you're going to combine with it is the one where the electrons are on the opposite sides to where the electrons are in the catalyst equation. So that's this red one here. So in order to combine them, we need to multiply up the iron equation, and then that will give us our first catalyst equation of S2O8 minus plus 2Fe2 plus goes to make 2SO4 minus plus 2Fe3 plus. You can then draw the other catalyst equation, the Fe3 plus turning back into the Fe2 plus. To do that, I'm just going to modify the catalyst equation that's already drawn. So we're going to have the Fe3 plus turning back, the Fe3 plus turning back into the Fe2 plus, and this time the electron will be on the other side. So the blue equation will now combine with this, so the electrons cancel, multiplied up by 2, so the electrons cancel, and so our second equation is going to be 2I minus plus 2 Fe3 plus goes to make 2 Fe2 plus I2. Later on in this video I'll show you a more complicated example of how to do this, but this is one of the catalyst equations that you need to know for the exam, but you can work it out as long as you know the separate equations. So auto-catalysis is where a reaction is catalysed by a product of the reaction. And before I show you an example of that, I'm just going to show you what the rate graph would look like. So we'll have time along the bottom, concentration of product along the side, and we'll start off with quite a slow rate at first, and so there's not much product will be formed. Then as the catalyst gets formed, the product will get formed quite quickly, and then it will tail off. So there are three very distinct parts of this graph. The first part is at the beginning, where there is no catalyst, so product forms slowly, and the reason why a reaction is slow is generally because the activation energy is high. Then reaction speeds up as catalyst is formed, and then at the top reaction slows down again as reactants run out, like it would in any other reaction. So the shape of that graph is the same for any auto-catalyzed reaction. And an example of an auto-catalyzed reaction is a reaction between manganate ions and ethane diode ions. Now, you will be expected to know this reaction, but you can work it out as long as you know what the reactants and products are. So your manganate ions are MnO4 2-, and they turn into Mn2+. And your ethane diode ions are C2O4 2-, and they turn into CO2. So we can balance those two half equations and then combine them together to form our full equation for this reaction. So the top, the Mn's are already balanced. We'll add 4 waters to balance the oxygens, add 8H+ to balance the hydrogens, and then add 5 electrons to balance the charge. In the bottom we need 2 in front of the CO2 to balance the carbons. The oxygens are now balanced, and so we need 2 electrons to balance the charge. And then we need to multiply the top one by 2 and the bottom one by 5, so the electrons cancel. So we'll do that. So the top will have 10 electrons, 16 hydrogens, 2 MnO4 2-, 2 manganeses, and 8 H2Os. And the bottom will have 5 C2O4s, 10 CO2s, and 10 electrons. And if we combine these, we get 5 C2O4 2- plus MnO4 2- plus 16H+ goes to make 10 CO2 plus 2 Mn2+ plus 8 H2O. Now, you'll notice that a transition metal ion is formed as one of the products, and you know that transition metals have variable oxidation states, and manganese is no exception. So manganese can exist in Mn2+ and Mn3+, and this is what is the catalyst for this reaction. The reason why this reaction gets quicker with the catalyst is because it's got quite a high activation energy due to the fact we've got 2 negatively charged ions reacting with each other. So we've got our 2 half equations up here already. Again, you are expected to know the catalyst equations, but you can always work them out as long as you remember that Mn2+ turns into Mn3+ plus an electron first. So the one this is going to combine with first, the reaction it's going to combine with, is this top one, because the electrons are on the right-hand side here and the left-hand side here. We may as well use the multiplied up equation to balance, so we'll multiply all these by 10. So the electrons cancel, and so you'll get 16H plus 2 MnO42 minus plus 10 Mn2 plus goes to make 10 Mn3 plus 2 Mn2 plus 8 H2O. And then your Mn2 pluses will cancel. The 2 on this side will cancel with 2 on here, so we'll have 8 Mn2 plus there instead. So that's your first catalyst equation. You can see you could divide it all by 2 if you wanted to make it simpler. And then, as before, your Mn3 plus is going to turn back into Mn2 plus. So we'll just do that here. So Mn3 plus turns back into Mn2 plus an electron, which is on the wrong side at the moment, sorry. That should be on this side now. And this time it's going to combine with the second equation, the second half equation of this full equation. So this time we need to multiply this up by 5, so the electrons cancel. Not 5, sorry, 10. So the electrons cancel again. And so this time you'll get 5C2O42 minus plus 10 Mn3 plus goes to make 10 Mn2 plus 10 CO2. And again, you could divide through by 5 in order to make this the simplest equation possible. And so that's how these are quite difficult to remember if you just try to remember them off by heart. You can, though, work it out if you know what. Basically, all you need to know is that manganate ions turn to Mn2 plus and C2O42 minus ions turn to CO2. And then from that, you can work out all the rest. So let's have a look at a few past exam questions on this. So first, state the characteristic property of transition metals that enables them to act as catalysts in redox reactions. The characteristic property is that they have variable oxidation states, which essentially means that they're able to gain electrons off one thing and give it to another thing. The fact they can gain and lose electrons over and over again makes them good catalysts. And then, in the contact process, the conversion of sulfur dioxide into sulfur trioxide, vanadium oxide acts as a heterogeneous catalyst. Write 2 equations how this catalyst is involved in the reactions. Those are the equations I said you needed to know. So SO2 plus V2O5 turns into SO3 plus V2O4, and the V2O4 reacts with half O2 to make V2O5 again. And then it's just one reason why poisoning reduces the effectiveness of a heterogeneous catalysts. Active sites are blocked. And then finally, suggest how poisoning of a catalyst used in industrial process can be minimised, and that can be minimised by purifying the reactant mixture. So this next question says, transition metal ions can act as homogeneous catalysts in redox reactions. For example, iron 2 ions catalyse a reaction between peroxide disulfate ions and iodide ions. State the meaning of the term homogeneous. So this is where the catalyst and reactants are in the same phase. And then suggest why ions from S-block elements do not usually act as catalysts, and that's because they do not have variable oxidation states. Write an equation for the overall reaction that occurs in aqueous solution between S2O8 2- ions and I- ions. So this is just one you have to know. So it's S2O8 2- plus 2I- goes to make 2SO4 2- plus I2. And then give one reason why in the absence of a catalyst the activation energy for the reaction between peroxide disulfate ions and I- ions is high. That's because they're both negative, so the negative ions repel each other. And then finally, write two equations to show how Fe2 plus ions can catalyse reaction between S2O 8 2 ions and I ions. Just one reason why activation energy for each of these reactions is low. So you can work them out like I showed you in the previous slides, but I'm just going to write them out. So you got first got S2O8 2 minus plus 2 Fe2 plus goes to make 2 SO4 2 minus plus 2 Fe3 plus, and then you got your I minus, two of them reacting with 2 Fe3 plus to make 2 Fe2 plus plus I2. And the reason is because the negative and positive ions attract each other. So final question, we've got an acidified solution of potassium manganate was reacted with a sample of sodium ethane diet at a constant temperature of 60 degrees. The concentration of the manganate ions in the reaction mixture was determined at different times using a spectrometer to measure the light absorbed. And there's the results. So it's the concentration of the reactants that was measured here rather than the products. And it says write an equation for reaction between manganate ions and ethane diet ions in acidic solution. So you can either learn the whole reaction off by heart, or you can just learn the conversions. That's what I'd recommend you do. So remember, you've got MnO4 minus going to make Mn2 plus, and your ethane dioate C2O4 2 minus ions make carbon dioxide, and then just balance each one. So you need 4 waters on the right here, 8H plus 5 electrons. And on the bottom you need 2 CO2 and 2 electrons, and then multiply top one up by 2 to make 10, 16, 2, 2, 8, and the bottom one by 5, so you've got 10 and 10, and then add them together to get the overall reaction. So you've got 5 C2O4 2 minus plus 16H plus 2 MnO4 2 minus goes to make 2 Mn2 plus 8 H2O plus 10 CO2. Try and make sure you write it all on one line like I haven't done there, just to make it clear. And then this reaction is auto-catalysed. Give the meaning of the term auto-catalyst and explain how the above curve indicates clearly that the reaction is auto-catalysed. The meaning of the term auto-catalyst is that a product of reaction also catalyses it. And then we need to explain how the graph shows that this reaction is being catalysed. And basically, the graph shows because the reaction starts off slow and then speeds up, and that's it. So reaction starts off slow and then speeds up. The auto-catalyst in this reaction is Mn2 plus, and then write two equations to show how the auto-catalyst is involved in this reaction. So remember, you've got your Mn2 plus turning into Mn3 plus an electron, and you got an electron plus Mn3 plus and turning it back into Mn2 plus. So this Mn2 plus and Mn3 plus one should combine with your manganate half equation. To do that, you need to multiply this up by 10, so you've got 10, 10, 10, so electrons cancel, so you'll get 2 MnO4 minus plus 16H plus 10 what will be 8 Mn2 plus once the Mn2 pluses are cancelled goes to make 8H2O plus 10 Mn3 plus, and then the second equation will combine with your ethane diode equation, so you're going to multiply everything up by 10 again, and so you'll get 5 C2O4 2 minus plus 10Mn3 plus goes to make 10Mn2 plus 10CO2.